Making your morning cup of coffee, mixing up a pre workout drink, or just cracking open a really cold soda, we do these things every single day, right? But what you're actually watching is physical chemistry in motion. Welcome to this explainer on the mechanics of solution, where we are going to unpack the invisible forces that dictate exactly how materials blend, mix, and transform. Here is a quick roadmap for this explainer. We'll kick things off with the basics of solutions, then we'll look at the vital difference between capacity and dissolving rate. After that, we dive into our speed accelerators, stirring and crushing, our capacity multipliers, temperature and pressure, and finally, wrap it up with some real-life solubility. All right, Section 1, the basics of solutions. Let's start right at the core with solubility. This is simply the baseline ability of a solute to dissolve in a given solvent. Before we even think about introducing heat or agitation or pressure, we really just have to establish if two materials are naturally compatible. The basic equation here is pretty straightforward. Solute plus solvent equals a solution. When you combine them successfully, a true solution becomes a homogeneous mixture, meaning those solute particles are perfectly evenly distributed right throughout the solvent matrix. Now, obviously, not all materials play nicely together. Soluble materials, like sugar or your powdered juice, they readily integrate right into that water matrix. But insoluble materials, think sand or plastics, they are not going to dissolve. It doesn't matter how much kinetic energy or heat you blast them with, it's just not happening. Moving on to Section 2, capacity versus dissolving rate. So here is where it gets really interesting. It is absolutely crucial to understand the distinct difference between capacity and kinetics. Capacity is all about solubility. How much can mathematically dissolve? It's the absolute maximum limit of solute that a specific solvent can handle before the excess just piles up at the bottom. Kinetics, on the other hand, is simply the dissolving rate. It's how fast that solute dissolves into the solvent. Think of it like a scale versus a stopwatch. The scale represents capacity. Maybe the water is totally saturated and literally cannot hold even one more molecule. The stopwatch represents kinetics, the vast difference between a powder dissolving rapidly in seconds versus a solid chunk taking hours. As we're going to see next, some of the physical levers we can pull only affect the speed, while others affect the whole shebang. Okay, Section 3, accelerators, stirring, and crushing. Our very first accelerator is agitation. Imagine a solid sitting unstirred in a liquid. What happens is it creates this heavily saturated solvent cloud immediately surrounding it, literally blocking fresh water from getting in. Stirring mechanically disperses those dissolved particles. It constantly replaces that saturated cloud with fresh solvent. But remember, this strictly changes the speed, not the absolute maximum capacity. Which brings me to a quick question for you. If you've got a dense sugar cube in one hand and an exact equal weight of crushed, granulated sugar in the other, which one is going to dissolve faster in your glass? Just think about that for a second. Well, if you guessed the crushed sugar, you hit the nail right on the head. Because solvents can only attack the exterior surface of a solid. Breaking that solid down exponentially unfolds it. You're exposing a massive amount of brand new surface area all at once, allowing the solvent to attack from every single angle. And again, this is strictly a speed accelerator. Section 4, multipliers, temperature, and pressure. Temperature is our universal multiplier when dealing with solids. Adding thermal energy gives particles much higher kinetic energy. Suddenly, those energetic solvent molecules are zipping around way faster. They're colliding with a solid solute a lot more frequently and with significantly greater force. This action literally expands the matrix, effectively increasing both the speed of dissolving and the total maximum capacity. But what about dissolving gases, like carbon dioxide? For that, we rely on atmospheric pressure. Unlike solids, gas solubility is driven almost entirely by external pressure, acting like a giant physical piston, trapping those gas molecules forcefully down into the liquid matrix. You see this every time you grab a sealed soda bottle. It holds the dissolved gas perfectly under pressure, but bubbles start escaping the literal second you twist off that cap and the pressure drops. Pulling this all together into an optimization grid really clears things up. If you want to maximize dissolving speed, you bump up the temperature, increase agitation, or crush the particle size. If you want to maximize the total absolute amount of a dissolved solid, you crank that temperature dial. And if you're trying to maximize dissolved gas, you rely on pressure. So speed has accelerators, solids have temperature, and gases have pressure. Simple as that. Finally, Section 5, real-life solubility. These invisible mechanics are literally powering our everyday world.
Dropping an effervescent tablet into water, that utilizes particle size for incredibly rapid absorption. Brewing a great cup of coffee relies on high temperatures to optimally extract those complex flavor compounds. Chemists are manipulating these exact same solvents daily to synthesize new materials. We even formulate our daily soaps specifically with chemical bridges so they can dissolve otherwise completely insoluble oils.
The big takeaway here is that mastering these four factors, temperature, agitation, particle size, and pressure, gives us incredible, tangible control over the physical world. It's what allows pharmacologists to design medicines that hit your bloodstream faster. It allows beverage companies to perfectly balance the bite of a carbonated drink. It lets chefs pull absolutely every ounce of flavor out of their ingredients. And hey, it's the exact reason you need hot water to properly brew your tea. It is practically applied magic, completely driven by physics.
So I'm going to leave you with this final thought. The next time you're just casually stirring some sugar into a hot cup of coffee, or you hear that satisfying little hiss from opening a cold soda, I want you to look a bit closer. Think about the kinetic energy in that cup, the surface area unfolding, the atmospheric pressure trapping those tiny gas bubbles. Ask yourself, what invisible mechanics are at work right there in your own hands? The whole world is basically a bustling chemistry lab hiding in plain sight, just waiting for you to pull the levers. Thanks for joining me on this explainer, and keep observing those amazing mechanics all around you.